do me the favor. Go back to the last podcast, the one just before this one, which was an introduction to absolute value functions. Watch it again. I really think you need to. There's so much information in there because I'm going to just start assuming that you know this and I'm going to fly through this podcast with you. Well, maybe not fly, more like jog. Okay, here we go. Look at this question. It says, sketch me the graph of this absolute value function. Probably the easiest way to do it is start just by the original graph. Don't absolute value anything. Just look at what the original graph looked like. Well, if you think about this, this is in the form of y equals mx plus b, something you did in grade 10, math 10c, okay? So what we have to do is we have to identify, yep, there's our slope, which is, of course, rise over run, right? And that slope is, in fact, 2 over 1. There's our y-intercept, our b value, which in this case is -6. So I'm going to go over here to -6 to my graph, and I'm going to put it down. There's my -6. I'm going to rise 2, run 1. Okay, rise 2 means 1, 2, run 1. There it is. And I'm going to draw me a beautiful graph that goes way out looking something like that. Okay, there's my original graph. Now, step 2 says here to reflect. Reflect in the x-axis, the part of the graph that is below the x-axis. Well, that's kind of like we did in the last question. If you go back into the first podcast here and look at that again, you'll see that we actually reflect it. Well, how do we reflect it? It's very, very simple. Look at this intercept here at -6. Think about that. When we do the absolute value of -6, does that not become 6? There it is. Here's the intercept, which is eventually what we're going to call our critical point, right? Or our vertex, okay? And we're just going to go from here, and guess what? Ta-da! There you go. There's your graph. From there and there, that's what your absolute value graph is going to look like. Oh, well, that's not so tough. That's actually pretty easy to graph. As long as you have your intersect here, your critical point, your x-intersect, okay? And you know what the original graph looks like, then you could take the absolute value of that and go, whoop, and you're done. Wow, that was kind of easy. But there's a little bit more detail to it than that. And I want to start talking about some of the details and some of the key words that you're going to see. One of the key words that you're going to see is something called invariant point. This is a point that remains unchanged when you do a transformation, like absolute value. So what is the one point that remains unchanged no matter what you do? Well, that in fact starts with your critical point. And then any value going over here that you have not changed. Think about it. When you absolute valued your original line, and remember your original line was this red thing right here that went up like this part of the graph did not change, okay? It was this section that changed. So these in fact are all invariant points. These are all points that have not changed. Okay, great, awesome. Okay, now look at this. It says determine the x-intercept and the y-intercept of our new graph. Well, okay, wait a second. The y-intercept was way too easy to determine. That y-intercept was this guy way down here. Remember, it was at -6 here, and all we did is took the absolute value of -6 and bopped it up to here. There's our new y-intercept. Well, that's not so tough. But now the question is, what is the x-intercept? Well, remember something. X-intercept happens when y equals to 0. Okay, so let's look at our original graph. Our original graph was y equals to 2x minus 3. So now we want to find the x-intercept, so just make that equal to 0 and solve. Bring the 6 over. 6 equals to 2x, divide by 2, x equals to 3. And in fact, if you look right here, dun, da, 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 right there at our critical point, it is exactly at 3. So our critical point in this case is 3, 0. Why 0? Because that the x-intercept is when y equals to 0. Great. Now, next, state the domain and range of this function. Well, wait a second. Hold on. Domain can be anything you want it to be. It's still an x is an element of the real numbers. X can be anything, right? There's no restrictions on the x. You can make x a negative, a positive, and then just absolute value the thing, and you should be fine. But how about the range? Well, the best way to determine range is look at the graph. Look at this graph. This new graph, which I put up here, boy, it's a mess, okay? This new graph right here, right there, look at it. It stops at the x-axis. There's no part of it down here. This has all been absolute valued. So if it's all been absolute valued, your range then is y has to be greater than and equal to 0. Of course, because it's been absolute valued. Look, the absolute value tells you you're absolute valuing the entire graph, making this whole thing positive. Nice. Now, let's do the piecewise notation for this. Now, wait a second. Let me clear this up a little bit. Let's clean it up. Let's see what we got here. Okay, perfect. Now, I'm going to do a quick sketch of this graph again. Remember, we had some critical points. We had this 3 here, which was our critical point, which meant our graph kind of looked like this. We also had a vertex up here, which is +6. But the most important thing about this is this critical point right here, because this is the part of the graph that was positive, that was fine. This part of the graph did not change. It was this part of the graph here that came from this value out here. This is the part that got flipped. So, okay, wait a second. How do I write that in terms of piecewise notation? Remember, you're dealing with an a value that was positive, you're dealing with an a value that was negative. Simple. Take this graph. The positive version of 2x minus 6 happened when x was, think about it, there's that value of 3. When it was greater than 3, out this way. When it was greater than or equal to 3, this graph was normal. This graph was fine. But it was when you flip the graph, when this occurred, this major flip here occurred any value after 3. So for any value less than that critical point 3, this entire graph was flipped. And that is your piecewise notation. Now, some people may be a little critical right at this point and say, well, you know, you do have that negative up here. You know, you should actually distribute that in. Fine. Let's distribute it in. Let's draw it like they want in your math textbook. Y equals 2. They'll do the entire line like that. What was the part that was not flipped? The part that was not flipped was from this 3 going that way. So the part that was not flipped was the 2x minus 6. That was the original graph. We didn't flip it. That happened when x was greater than or equal to 3. The part that flipped, and we'll just distribute that in there now, giving you minus 2x plus 6, was the part that was x less than 3. Now, do you remember the intersect? Do you remember? Here is the graph. Oops, sorry. Here was the graph right here. Okay, and remember, we had an intersect at +6. Look, it was originally -6, now becomes +6. Check this out. This slope is downwards with an intersect at +6. Look, the slope is downwards with an intersect at +6. That, in fact, is this portion of the graph. This portion of the graph is right there. Isn't that cool? Now you know a lot about piecewise, and you know a lot about doing this kind of graphing.